Okay, so welcome back to chemical reactor theory, and we've finished module 5 in the previous class. Now we are going to start the new module, and this new module is fluid solid non-catalytic reactions. Okay, so these might include things like solid dissolution. It could include burning of coal. uh, it could include various metallurgical reactions which involve ores to metals. Anything that involves a solid and that's reacting in either a gas phase or a liquid phase reactant. So these would be examples of gas solid non-catalytic reactions. There's one more type of reaction that's also an example of gas solid non-catalytic reaction, and that is basically if you have a catalyst pellet, what we have done in the previous module, and let's say that pellet has got deactivated. Okay, now that deactivation could be because of coke formation, it could be because of some deposition of some other species and so on. Okay, so if you have gotten a catalyst pellet that has, let's say there's coking that has happened, so then the removal of coke or decoking is also another example of a non-catalytic reaction. Okay, so these are various examples, and we'll look at how to handle these type of systems. So for further reading, it's basically Froment and Bischoff chapter 4. That's the main chapter from which all of the material will be derived. Okay. Now these types of systems are analyzed in two parts when it comes to analysis of the system. The first part is to treat it as a fluid solid catalytic or fluid solid system. Okay, that means whether there is internal resistance, external resistance and all that. So that is looked at. So that talks about how the reaction takes place within the pellet itself or on the surface of the pellet. Okay, thereafter, because of the reaction that is taking place in the pellet, whether it is a catalyst pellet that is undergoing decoking or whether it is any solid that is undergoing reaction, because of that reaction there is a change that happens in the solid. Now this is where this particular module 6 differs from the previous module. In previous module, what did we have? We had that the catalyst pellet itself did not undergo any change, whereas here the difference is that the catalyst pellet or the solid pellet is going to undergo some change. Okay, now let's think about the same case of a porous pellet. Okay, and let's say there were active sites. Okay, now when we performed any reaction in this system, okay, after performing the reaction, the pellet remained pretty much exactly the same. There was no change that happened really in the pellet. Okay, so what we really analyzed was how the gas phase or the liquid phase species they change with time. Okay, we did not have to worry about the solid changing at all. It was only the fluid reactants and products that were undergoing any change. Okay, as against this, if the situation is, let's say you have this catalyst pellet that that's gotten coked. Okay, so let's say that coke has deposited over here. Okay, okay. So let's say that coke has gotten deposited, and let's say now we are burning off that coke using oxygen, right? So when it comes to gas phase, the reaction proceeds more or less in a similar manner, just how we analyze the system in the previous module. because there's diffusion that is going to take place, there's reaction going to take place. So there's external diffusion, there might be internal diffusion plus reaction taking place. But what happens to the solid itself is as it is reacting, okay, as it is reacting, the coke itself starts getting consumed. Okay, so after a while the snapshot is going to look, something like this, where some of this has gotten consumed. Okay, so now the outer layer of coke that has gotten consumed, now more reaction takes place, internal some more coke disappears. Okay, and initially what was happening was right from the edge of the particle you had decoking reaction happening, but now what is happening is that your oxygen has to diffuse within the pellet without any reaction taking place, and only after that the reaction is taking place. Okay, so what is happening is over time the nature of the solid itself is undergoing slight change, and that needs to be accounted for. Okay, so one is a snapshot picture of what is happening to the gas phase is going to remain unchanged. The analysis is going to remain unchanged from what we did in the previous module, but what is happening with the solid, that analysis keeps changing. Okay, so this is an example of a decoking of a catalyst particle. Okay, another example could be, let's say you have, let's say, a copper slab, and that copper slab is undergoing a reaction. Okay, let's say we take metal or copper and dip it in sulfuric acid, it is going to undergo a reaction. Okay, so or have you ever been to these uh, jewelry shop where they clean silver jewelry, right? They get rid of the, of course they scrub it and all that, but let's say it was not being scrubbed, it was just your silver jewelry was put inside inside that liquid. Or you might have seen those ads of Brasso. What does Brasso do? It gets rid of the oxide layer on top of brass. Yes, no, you not heard of Brasso? Okay, so yeah, at least when I was a kid, there used to be a lot of ads for that. So what is happening over there is, let's say this is silver or brass, and that has a small layer of oxide that is present. Okay, so what happens in a case like this is, as your reacting fluid reacts, it takes away, it peels away layer by layer. Okay, so the external layer is the one that first reacts. Okay, so it's not a porous material, but the reaction is taking place on the surface only. So there's no internal diffusion, there's only external diffusion. Okay, other example would be rusting of iron. What happens when the iron gets rusted? The ferric oxide that is actually formed, the oxide layer is very porous. So you basically have, you know the metal over here, and that is topped with a highly porous layer of iron oxide. Okay, So when this iron oxide is there, at that time there is no reaction taking place in the iron oxide layer. Your oxygen diffuses through that layer and the reaction is only taking place on the surface. Okay. So we now have different situations. One case in which diffusion is taking place within the solid, and as the diffusion takes place, reaction is happening. In another case, we have there is no internal diffusion taking place, there is only external diffusion taking place and the reaction is happening on the surface of the solid. We have a third case when the diffusion is taking place, but the reaction is happening again on the surface itself. Okay. So in the reactive part, this is the example. In the reactive part, the reaction is happening only on the surface. In the reactive part, reaction happening only on the surface. In the reactive part, reaction is happening along with diffusion. Okay. Other case is that there is diffusion that takes place internally and reaction that is taking place. There is no internal diffusion, only external diffusion is taking place, and there is internal diffusion and external diffusion, but internal diffusion is without a reaction. Okay. So as you can see, there are different situations based on the type of examples that we are going to look at. Okay. Okay. So in the previous module, what we considered is a diffusion and reaction within the particle and outside a particle. Okay. We had external diffusion, we had internal diffusion, okay, and we would have internal diffusion with the reaction. So those were the various cases that we encountered. What we did was, when it came to external diffusion only, we got an expression of this type for first order reaction if the reaction is taking place on the surface. If we had internal diffusion, then we obtained the R net as some function of R internal, okay, and that function is expressed through effectiveness factor eta. Okay. So that is what we had done in the previous module. Okay. In this module, what we are going to do is to look at fluid solid non-catalytic systems. Okay. The processes, as I said, processes with respect to the fluid phase remain similar. Okay. No change in the fluid phase. So if there is external mass transfer limitation, there would be external mass transfer limitation here also. If there is internal mass transfer without any reaction, you remember I talked about composite pellet very briefly in the previous module. Okay. So there might be internal diffusion without any reaction taking place, okay, and then there is internal diffusion with reaction that is taking place. Okay. But unlike the catalytic case, the solid reacts, and the solid reaction may either result in no change in the particle size, which was the case over here, or which can result in a change in the particle size, or it can result in no change in the particle size but a significant change in how porous that particle might be. Okay. So all these cases need to be considered as well. Okay. How to consider that, how do you analyze it, and so on, for certain illustrative ideal cases we are going to do in this particular module. Okay. So now the difference between catalytic and non-catalytic is, one most important difference is because the solid particle is undergoing change. So non-catalytic processes at the scale of the reacting particle are always unsteady. Okay. The processes at the level of gas, okay, we take a snapshot and we assume it to be steady. Is it steady? It is not steady, but we assume a pseudo steady state type of an assumption. Why? Because gas phase processes are significantly faster than solid phase processes. Okay. That helps us simplify our analysis. What it means by that, what I mean by that is, let us say this is the snapshot that we are seeing. Okay. Then we will say that maybe the outer 20% is non-catalytic, inner 80% is catalytic. Let us just do a gas phase simulation based on that. Let us not consider transient gas phase. Okay. Let us say after that 5% more reacts and 75% is catalytic and 25% is non-catalytic. Again we will assume a pseudo steady state in the gas phase and use the analysis that we did in the previous module. Okay, that is how we are going to approach this. Okay, it might be a little bit confusing now, but we'll go over this step by step. Okay, but before doing that, let's open the floor for discussion. And I talked about a few examples involving solid and fluid reactions. Okay, one reaction was decoking. And other was rust. What other examples of solid fluid catalytic reaction, non-catalytic reactions can you think of? List it out. It will be easy 1-mark question for your final exam. Oxygen concentrator. Adsorption base. So you have zeolite beads and the zeolite beads keep absorbing oxygen. Likewise, we could also say CO2 capture. Same concept, or CO2 release as well. What else? Burning of coal. I don't know which one you meant, but if it is burning, it's camphor plus O2 giving CO2 plus H2O. If it is sublimation, camphor solid leads to camphor gas. Okay. Strictly speaking, the latter or oxygen concentrator, strictly speaking, might be a physical process, but the analysis is done exactly the way we do CRE type of reactions. What else? Illyridial depends. Illyridial, if the standard illyridial that we talked about in module 4 will be gas solid catalytic reactions. So therefore, the nature of the catalyst doesn't change. There is, but that's a very good question because there's another mechanism called Mars Van Krevelen. Okay, again I'm putting it in squiggly brackets because it's a little bit more complex. What Mars Van Krevelen mechanism is basically like your Langmuir-Hinshelwood or your illyridial mechanism, but the difference is the species that we are talking about, one of the reactants, let's say O star that we are talking about or H star that we are not talking about, is not an adsorbed species, but it is a lattice species. So for example, one of the catalysts that we use is cerium. Okay. Now ceria is a reducible metal oxide, so it can go to C +2 and +3 and +4 stage oxidation states. Okay. So when ceria goes to this, it will release half O2. Okay, and this O2 can be used in oxidation. Okay, so it's a redox catalyst. So So in the reduction cycle, it will give up oxygen, and that oxygen can react with any species, and in the oxidation cycle, it will take up oxygen and Ce2O3 will go to CO2. Okay, there are several catalysts like these, and they are very useful in reactions called as chemical looping reactions. Okay, what happens in chemical looping is you will have reduction cycle followed by oxidation cycle. So you will have oxidized ceria reacting, let's say, with carbon monoxide to give CO2, and in the next cycle you will have Ce2O3 plus oxygen giving CEO2. So that's done a lot. One of my students is working on nickel ceria based catalyst for looking at oxidative dehydrogenation type of reactions. So right now we are looking at CO2 as a mild oxidant, but it has also been used for a for oxygen storage mechanism. Okay, ceria, for example, in your car catalytic converters is used a lot for storing oxygen whenever there are oxygen lean periods. So for example, let's say in stop and go traffic, suddenly if you brake, what happens is the combustion is very inefficient, because the fuel that was taken inside the engine is not combusted anymore to give power, but it is combusted just because the engine is hot. So it will reach, instead of reaching 99.999% conversion, it might reach 99.9% conversion. So there will be some amount of hydrocarbon that will be left. Now that hydrocarbon does not usually have enough oxygen to get completely removed. So you would have ended up seeing smoke. So every time a car brakes, if ceria was not there in the catalytic converter, you would have seen smoke every time a car brakes and every time a vehicle accelerates. Okay. In the old vehicles, you would have seen it during vehicle acceleration, that's the smoke coming out, right? This is the presence of what is called as a particulate filter that prevents the smoke from coming out, and its presence of ceria that prevents hydrocarbons from coming out whenever you have a braking event. Okay, so and that particle filter also, when you do, how do you regenerate? So what happens to the particle filter? You have particulate matter that gets trapped inside the filter, and every say 2 minutes, 2.5 minutes, you regenerate that filter. How do you regenerate? By burning off these particles. Okay, just a little bit of excess of fuel is taken in, a little bit of excess of oxygen is taken in, and that is allowed to pass through this catalyst filter, and it will burn off whatever coke is being formed. And that is another example of decoking, but that's not a decoking of a catalyst, it is just decoking of a filter. Okay. Which is also what, for example, some of your RO filters do. Not RO so much, but ultrafiltration. Okay, periodically there will be a very short cycle which will be a cleaning cycle. Okay. Okay, what else? Solid dissolution. Solid dissolution is one more. And again, talked about magnesium carbonate. So you do have, for example, soda lime and other materials that are used for CO2 capture. Okay, so that is basically, this is CO2 capture on an adsorbent. So that's a physical CO2 capture. Other thing is you have alkali. Okay, the most common material that is industrially used for CO2 capture is monoethanolamine. It's a liquid. The problem with which is something that we will do in the next module. The problem with monoethanolamine is regeneration is very expensive. Okay, so instead people are looking at solid based alternatives to monoethanolamine, where it could, for example, be calcium oxide converting to calcium carbonate, magnesium oxide converting to magnesium carbonate, soda lime converting to sodium and calcium carbonates, and so on. Okay, those are other materials which will involve CO2 reacting with an alkali or an alkali earth metal, leading to carbonates. What else? Okay, so I would expand it to say from ore to metals or non-metals. Ores to metals are more common. What about this? Yes, no? What's IGNOU? You know IGNOU, right? No. Yeah. Okay. So IGNOU is basically powder, but you also get it in pelletized form, seltzers, Alka seltzer and so on. So you just drop that pellet inside water and then it effervesces to go to give you basically alkaline, and there's gas that gets liberated. So if you drink that water, the alkaline part helps with increasing the pH of your stomach, and the gas induces burping so that you feel a little bit better. So the gas that gets trapped in your gastro tract gets released because of the CO2 that is being generated, and the alkaline part is reduces the acidity or increases the pH of your stomach. So that's used for an instant relief from acidity. Right. Okay. What else? Have you seen YouTube videos? Mentos dropped in Coke. Another example. Okay. Any other examples? Leaching. Rusting of iron, or more broadly corrosion. Why does iron get rusted but let's say aluminum does not, or silver does not? Yes, oxide layer is formed. So what? Iron rusting also oxide layer is formed. Sulfur, sorry, not sulfur, silver corrosion also an oxide layer is formed. But why are those two different? Sorry? Reactive? What is reactive? Not reactive. What is not reactive? The oxide layer. Yes, that's partly a reason, but mostly what's the difference between rust? Have you touched rust with hand? How does it feel? Have you touched layer of oxide on aluminum or steel? Not steel, silver. How does that feel? Not slimy, but it's not. So the oxide layer on iron is porous. Okay, the one on silver or brass, it forms a patina. Patina basically means a layer that is not diffusive. Okay, so that layer protects aluminum or brass. Okay. In case of aluminum and brass, it looks, in aluminum it looks gray in color, in case of brass it looks green in color, and therefore you periodically need to wash it away with brasso or equivalent stuff. Okay. Whereas when it comes to silver, it's when it is the sulfides that are formed that lead to a black coloring. Okay, oxide only gets rid of the shine on the surface. Okay, because it's a very thin layer of oxide that is formed, and it's a very slow reaction process, whereas sulfide formation is a relatively fast reaction process. Okay, but whether it is formation of oxide layers, that's corrosion, or whether it is getting rid of that oxide layer, it's still fluid solid reactions that are taking place. Okay. A couple of things that, yeah, so combustion of coal and charcoal you have said, gasification and pyrolysis, those are also gas solid reactions. Okay. Reaction, dissolution and particles, we said that. Treatment of ore, we said that. Regeneration of porous catalyst, we said that. Okay. Ion exchange is another thing that we missed out. Ion exchange is not very different from this. In fact, lot of oxygen concentration concentrators are also ion exchange devices. Okay. So, these are the examples of reactions involving solids and fluids. Okay. Often the dissolution of a particle, often it is on the surface only. Okay. Ore treatment, porous, so internal reactions also, but ore size changes. Okay. Regeneration of catalyst, but internal diffusion is taking place. Same thing over here also. Okay. Gasification, pyrolysis, it is usually similar to this case. Okay. So, broadly speaking, the cases that you will have is, the first case is reaction and dissolution of particle. You have this particle of this size, the particle size keeps changing. Okay, and the reaction is taking place on the surface only. Case number 2 is where it is porous and the size keeps changing. Okay. And third case, okay, the size does not change. I am just showing one pore, I am not showing multiple pores. So what happens is that the pore is completely covered with something, and then slowly the things within the pore react. So these are the three idealized cases. There are other cases also, and that is where the porosity of the particle significantly changes as the reaction is taking place. For example, when it comes to treatment of ore, that would happen quite often. Is not only is the particle, not only is there internal diffusion taking place, the reaction doesn't only take place on the external surface, it will take place on the external surface as well as in the pores. Okay, so the size will keep shrinking, but the pores will also keep getting expanded. That's what you see when ENO dissolution. Okay, or if you take an ENO tablet and dissolve it, it will as water seeps in, it will start reacting from inside out also. Okay, so that is going to be very complex to analyze, but these are the three situations that we will analyze. One, where the reaction is taking place only on the surface and the size is shrinking. Number two, where the reaction is taking place within the pores and the size does not change, or that's rather number three. And number two is reaction that is taking place within the pores and the size of the overall particle keeps shrinking. Okay, so these were the three processes that that I talked about on the previous slide. Okay, okay. So let's look at what we have analyzed before. If the reaction is taking place only on the surface, what analysis did we do in module 5? External diffusion, the reaction was K dash CAS. Okay, reaction plus internal diffusion. What did we do? What type of models did we use? Hmm? Right? What's the model over here? If there is no reaction inside the slab. Yes? It is just diffusion, yes. Just internal diffusion without reaction. What's the model? Just a weekend break and everything is forgotten, huh? RA will be 0. Okay. What if we have what will we have then? Very similar to the first situation, but with some difference. It's a mix of situation 1 and 3. What would you have? Same diffusion equation for blue. And one of the boundary conditions, or what is happening on the surface, is minus k dash CAS, which will equal the diffusive flux. Okay. So, you can either solve, as he said, you can either solve it as a boundary condition on one surface. Okay. Remember, one of the boundary condition that we use outside is CA equal to CAS. I will write it as CAS2 or call it CA cat. Okay. Earlier, what did we say? That the boundary condition at the top was CA equal to CAS, at the center was del CA equal to 0. Instead, over here at the other end, del CA is going to be equal to rate of reaction. Okay, that is going to be the boundary condition. Or alternatively, you can do the analysis exactly as you did earlier. CA at the top, rate of the top concentration is CA S, at the bottom concentration is CA cat. Okay, rate of reaction at the bottom is equal to K multiplied by CA cat. Okay, remember what you did earlier in external diffusion, Kc multiplied by CAB minus CAS equal to rate of reaction. A similar thing you will do over here as well. Not the exact same thing, a similar thing. Why could you do that exact same thing? Because your slope was constant. Here, if the slope is not constant, you will have to take the appropriate slope at the edge. Okay. So, these are the things that you have done in module 5 already. This is what we are going to start off in the next lecture. We will start talking about external diffusion when the solid is non-porous, external and internal diffusion when the solid is porous, and do the analysis as we have done in module 5. Okay. What if the slab is porous and the reaction is taking place on the right surface? Then how do we do the analysis? What if you have composite slab? How do you are going to do the analysis? Okay. All of these are basically trying to link module 5 with module 6. We are going to use the concept of module 5 in module 6. Okay, that is what we are going to do in the next lecture. Okay, alright, all these notes are already uploaded, and please read ahead with your Froment and Bischoff chapter. Okay, right, I will see you in the next class.